Faster than the space-time fabric can handle. If you keep up with it, it will just tear. Right now, I'm terrified by this. The night sky is rapidly changing, and in only a matter of years, if not decades, it could completely vanish from view. Around the world, astronomers are sounding the alarm. Alarmists such as Neil deGrasse Tyson have recently announced Polaris's explosion, and the story behind Polaris is quite frightful. Long ago, the North Star remained constant in the night sky, serving as an important point of reference for astronomers and navigators. However, this might alter our night sky in the near future, and measurements made by the stars could change forever. Let's investigate the significance and impact of this threat and its implications for all of us. So come along as we discover the Polaris story, as Polaris is coming to an end for centuries. Polaris has advised astronomers and mariners holding a position of respect. Providing a beacon with its unwavering presence in the heavens has been crucial for navigation, but that stability may soon be affected. In a September 2023 research paper presented by the respected Royal Astronomical Society, the fate of this star of the heavens was questioned. Polaris is about to burst into flames, possibly disappearing from the night sky forever. Before we investigate the repercussions of this revelation, let's learn more about Polaris, known as the star at the pole or the North Star, because it is so close to the North Pole of the universe, just a little above Earth's North Pole. Polaris appears almost stationary in the northern sky. In the constellation Ursa Minor, or the Little Dipper, Polaris shines as a moderately bright yellow-white supergiant star, which is much bigger and brighter than our Sun. It is not a single star, but part of a complex system of 3 stars. With Polaris A forming a binary pair, they are orbited by Polaris B. The interactions between these stars result in gravitational forces that shape their behavior in orbits. Any changes in these interactions can result in sporadic variations in the star's brightness or pulsation patterns, but the specific mechanisms behind these interactions remain unclear. Polaris is about 323 light-years from Earth, which means the light we see today began its journey more than 3 centuries ago. If Polaris exploded now, we wouldn't observe it for more than 3 centuries. It's even possible that Polaris has already exploded, but we haven't observed the light produced by that event. Throughout history, the North Star has possessed significant cultural, navigational, and symbolic significance. Due to its fixed position, it was of great assistance to ancient navigators, leading them across land and sea. Symbolically, Polaris represented stability and guidance, remaining unwavering in the ever-evolving night sky. For astronomers, Polaris was a crucial reference point that aided in the study of space and time. As a Cepheid variable star, Polaris's periodic changes in brightness have provided valuable information about stellar properties. The nature of variable stars has also played a significant role in determining distances between stars, and these pulsations, used during instrument calibration, adhere to an established pattern. This made it easy for us to predict how Polaris would act. However, Polaris has recently deviated from this expected behavior. Its pulsation cycle is irregular, leaving astronomers perplexed and leading to a closer investigation of this cosmic anomaly. Rather than the usual predetermined pattern, Polaris is now showing erratic cycles of brightness and dimming. Now, scientists are expressing worries that the star might be nearing the end of its life. Its behavior is consistent with that typically found in stars nearing their conclusion. The gradual lengthening of Polaris's pulsation period, which we have observed as a yearly rise of 4.5 seconds, may seem insignificant but has significant repercussions. Some astronomers think gravitational interactions among the stars in Polaris's system could be responsible for these shifts in its specific atmospheric conditions, affecting the patterns of its pulsations. Others are more worried, believing the star is close to going out of control. The parallels between Polaris's behavior and that of Betelgeuse, a notable star in the constellation Orion, are striking. Both stars have demonstrated baffling inconsistencies in their luminosity, posing questions about their potential for explosions. Typically, stars in their twilight stages display such routines before reaching the culmination of their evolutionary histories. While NASA has voiced greater concern regarding Betelgeuse, similar concern has not been explicitly targeted at Polaris. However, as a visible star approaches the end of its life cycle, it moves through several stages, including the main sequence, the red giant phase, and, eventually, a supernova explosion. The irregular pulsations of Polaris suggest it has entered the typical helium depletion phase, indicating that the star is nearing its end. These irregularities align with evidence of Cepheid stars going through their twilight, but definitive signs that Polaris is approaching a supernova remain inconclusive. Astronomers are focusing their attention on these anomalies to comprehend. What would happen if Polaris went supernova? Would likely be a spectacular event in our skies, outshining the moon and becoming one of the brightest objects visible for days, weeks, or even months. This could significantly alter how we view familiar astronomical objects like the Big Dipper or Ursa Minor, of which Polaris is a part. You can rest assured that Earth is most likely perfectly safe in the event that Polaris explodes due to its size and distance from us. While an explosion from Polaris would be as visually stunning as that of Betelgeuse, it might still be visible to the naked eye for a considerable amount of time and captivate astronomers who study nearby stars. Observatories would unquestionably observe this intriguing event, inspiring the community of scientists and astronomers worldwide. However, the particular impact and visibility on Earth's environment or atmosphere would be of lesser significance than a closer supernova event. But what about Polaris itself? What will become of it following a potential supernova event? Whereas giant stars typically end their lives in a supernova, this is unlikely for Polaris. When a massive star explodes, it undergoes a catastrophic core collapse, resulting in a powerful shockwave that causes the star to violently explode. However, Polaris is not massive enough to undergo such an explosion. Instead, when Polaris runs out of nuclear fuel, it will shed its outermost layers and become a white dwarf. This change will not result in a supernova, but rather a tranquil conclusion. Forming a small and dense stellar remnant, a white dwarf is the surviving portion of a low or medium-sized star that has used up its nuclear fuel. It has a very high density, about as massive as the Sun, but smaller than Earth. When this occurs, we won't be able to see the remnants from our planet, similar to how we observe the star today. Comparing the anticipated outcomes of Polaris's eruption with past supernova occurrences provides useful information about the formation of stars and their final fates. Contrasting our hopes with well-known supernova like SN 1054 or SN 1987A, SN 2014J offers valuable insights. Comprehending the potential outcomes of, for instance, Polaris's burst, SN 1054, led to the development of the Crab Nebula, a nebula that never stops growing and spreads radiation across numerous wavelengths. Providing astronomers with a wealth of similar fields of study, SN 1987A, observed in the Large Magellanic Cloud, provided information about the processes of nucleosynthesis dynamics, observing phenomena using supernova remnants, like the development of nebulae, the release of cosmic rays, and variations. Illuminance offers insights into these processes. Unique features of Polaris and nebula structures, like the Crab Nebula, result from the material's removal during the supernova explosion, which interacts with the interstellar space around. Gas and dust that add heavy elements and cycle-related contributions to stellar birth and death. In addition, the emission of high-energy cosmic ray particles, accelerated by the shock of a supernova, has astrophysical implications for wave processes and radiation in space environments. To arrive at a final comparison, scientists assess differences in the makeup, mass, speed of the materials ejected between the anticipated Polaris burst and other observed events, necessitating research into the spectra and remnants light curves from these occurrences, and predicting comparable defining characteristics of Polaris's expected burst. Determining whether the Polaris burst may result in the formation of distinct nebulae or the distribution of elements enhances our awareness of potential outcomes. Another important aspect of the investigation involves taking into account pulsational stars with decreasing variability stages like Polaris, against what was observed in supernova precursors like this one. analyses can help find patterns or deviations and offer an understanding of the variability in the burst's pulsational nature. Stars nearing the end of their life cycles could signal internal unstable conditions or imminent catastrophic events that provide clues about the evolutionary processes leading to supernova explosions. Despite meticulous observations and in-depth research, astronomers are left perplexed by Polaris's irregularities in behavior. Figuring out the unique conditions driving these anomalies holds the key to enhancing our understanding of stellar evolution. The mechanisms responsible for the irregularity of Polaris's pulsations call for multidisciplinary thinking, cooperation, and the development of sophisticated conceptual models and observational techniques. The potential loss of Polaris as an important reference point in the night sky raises significant concerns regarding astronomical projects. Ground-based telescopes and stellar measurements would necessitate adjustments that affect the accuracy of astronomical assessments. Navigation reliant on celestial landmarks, as well as cultural practices and systems, may also be affected by Polaris's absence. Emphasizing the significance of this cosmic occurrence, the mysterious actions of Polaris underscore the need for more in-depth, specialized investigations and research efforts. Astronomers must confront the complexities surrounding erratic pulsations to provide concrete responses that acknowledge the significance of comprehending the complexities of space-time. Ultimately, the solution to Polaris's fate remains a mystery, and only time will reveal its true nature. The pursuit of understanding and knowledge, despite cosmic unpredictability, is a testimony to humanity's unwavering efforts to decipher the mysteries of the cosmos. As astronomers continue to monitor Polaris, the peculiar star's behavior inspires a deeper investigation into similar stellar phenomena, particularly stars exhibiting irregular dimming and pulsations. Enhancing cycles is essential. By examining these stars, scientists can learn more about the mechanisms causing these irregularities and their potential outcomes. These observations can improve stellar evolution models and offer more precise predictions regarding the cycles of stars like Polaris. For example, technological innovation and the use of observational methods play an important part in these studies. Advancements in telescopes with greater sensitivity, along with space-based observatories, permit better measurements of stellar brightness and pulsation patterns. This technology has enabled astronomers to spot minute shifts in stars that were previously out of reach, resulting in a deeper comprehension of their actions and fate. In the end, one aspect under investigation is the role of shaping interstellar environments. The way stars behave right before the end of their life cycles and how they interact with the surrounding interstellar medium may influence observed properties. Studying these interactions helps scientists understand how a star's environment may influence its evolution and eventual transformation into a white dwarf or supernova. In addition, the repercussions of a potential Polaris explosion on cosmic bodies and other celestial phenomena are an area of interest. The shock waves and debris released from such an event could impact nearby planetary systems, stars, and even the creation of new stars. Comprehending these potential outcomes provides a more complete picture of the universe's workings and highlights the interconnectedness of diverse astronomical occurrences. The scientific community remains dedicated 2. Dissecting the mysteries surrounding celestial phenomena like Polaris. Collaborative efforts across institutions and fields of study are essential for expanding our understanding of the universe. Search for answers about the fate of Polaris and the broader implications of its actions highlights the significance of ongoing investigation and the endeavor to comprehend the dynamic, ever-changing cosmos. In addition to focusing on specific stars like Polaris, research centers on enhancing conceptual models that explain massive and variable stars. These models incorporate a variety of observational data sources, such as ground-based telescopes, laboratory experiments, space observatories, and simulations of stellar conditions. Bringing together diverse datasets helps improve our comprehension of the processes controlling stellar evolution, including the intricate interactions within multiple star systems and binary systems. Astronomers are also exploring how stellar explosions could impact cosmological phenomena, like galaxy distribution and the formation of heavy elements across the universe. Stars like Polaris greatly aid in seeding the interstellar medium with elements essential for planet formation and life. By researching these occurrences, scientists hope to learn more about galaxies' life cycles and the chemical enrichment of the universe.